Hi, my name is Iain Moncrief. I'm a student at Oregon State University, and I'm interested in programming languages and math. Last summer, I was on the Chapel team as an intern, and the the research question I I was tasked with, I guess, was is Chapel a viable option for machine learning problems? And can it be applied to can you write machine learning programs in Chapel and have it um, be competitive with other like state-of-the-art systems like PyTorch or like TensorFlow? So my task was to implement a machine learning or a set of machine learning tools and assess challenges with the Chapel language and utilize the parallel constructs that Chapel offered. So the result of my summer was I made a machine learning library, pretty basic. It was completely written in Chapel. It didn't use any sort of auto differentiation system like a PyTorch or TensorFlow. It but it provided a similar interface to like PyTorch does, where you have these layer classes and then you compose those together to make a network instance. Um, yeah, so all of the forward propagation and back propagation methods for those layers were hard coded. They didn't rely on an autograd system. So um, and yeah, if you don't know what autograd is or auto differentiation, it's basically a way for programmers to construct expressions or values out from tensors, um, and then automatically compute the gradients with respect to the components. It makes it really easy to make like machine learning uh, like networks. Um, so in my library, I implemented a tensor utility library, um, and it was kind of like a wrapper for Chapel's arrays, and I tried to utilize as much as possible Chapel's parallel programming constructs, like using for alls whenever possible and for each loops. And the library was sort of analogous to like a naive Python implementation using just plain NumPy. So, and it was also written completely in Chapel, so it wasn't like the most optimized, but it was sort of just like a proof of concept that you could write uh, machine learning programs in Chapel. And so yeah, the result was I was able to classify the MNIST data set using a convolutional neural network that I implemented using the library. And it could also do like basic perceptron classification, like classifying the XOR truth table and whatever. So this is a neural network. It has layers, which are the blue, and it transforms inputs to outputs. Each layer, yeah, it modifies it's like input tensor and then feeds that to the next layer. And so the input gets modified as it goes through the layer. And then when it gets the final layer, you get this, like, in this case, it's like a probability distribution of digits, 0 through 9. And its success or failure is propagated backwards then through the network. So this was the forward propagation step. And then adjusting the network to better give a better output is the backward propagation step. And this is like a more complicated example. Theta 1, 2, and 3 are like vulnerable parameters, so that's what is in each layer that's like the state of the network, but it gets modified during training. So you feed the digit 4 through this network, and then you feed it backwards, and then the next time it's more likely to predict 4 correctly. I won't go into this, but so when you train a neural network, there's a process called batch training, which it makes it gives you better results. And the part of batch training is you have a data set that you want the neural network to learn, and so you partition the data set into batches of the same size, and you run so you go through batch to batch, And in each batch, you feed the input of, or the data sample through the network, and then you feed you feed all of the samples in the batch to the network, and then you train on that batch. So you do the backpropagation for each batch, but you feed all the samples in the batch through the network. So if you have a batch size of 3, then it's like images. So you feed 7 in, then 4, and then 8. You can do all of this in parallel. So that's how that's one of the parallelism constructs that I use in Chapel. So you have a batch, and this is your layer, and you have a batch of inputs. So what happens in my library is the batch gets split up into its inputs, and then in parallel, all of the inputs are ran through the network, um, or given to the layer, and that gives you a collection of outputs, and then those outputs are recomposed into the batch, into like a tensor, and that's fed to the next layer. So yeah, everything in this square is run in parallel. Another way to see this is, you have a batch of images, and each horizontal slice of the network is just an instance of it running on a different input. So the batch moves in lockstep through the network, and then it gets to the end, and then backpropagation is run. So the other part of my project was to assess what parts of Chapel make it easier or harder to implement these algorithms. The most notable challenge, I think, um, is so Chapel is really, it's all about arrays and domains, and that's really, it offers a lot of power. You can do a bunch of like array operations just by considering the domains, but sometimes a lot of these algorithms don't they kind of, they're better written if they abstract over the domain, I guess, and they only really are specific about the dimension of the tensor. So suppose you have a function that you want to declare that it should only accept vectors. So the parameter is it's an array of real numbers, and it has rank 1. So you'd use a where clause to specify that. But then
Hey,
also,
Luca, I hate to have to cut you off, but I want to make sure that there's time for questions, and
oh,
we are just at the 8-minute mark.
okay, sorry about that. All right.
No, you're
Yeah.
totally fine.
Okay. Anyway, so I made a tensor class that you won't need to specify the dimension, and yeah, that made it sort of easier. And the benefit of the main benefits of Chapel is it's just easy parallelism. You don't really have to think about that. Um, and this is a performance comparison that I did. And I'm returning to Chapel in the summer, and I hope to build off of what I did last year. And that's all. Thank you also to Daniel, Lydia, and Brandon for helping me with my slides. Any questions?
Awesome. Thank you so much. Is there any questions in the chat or anyone else who have a question? If not, I have a quick question for you, which is, given the talk about GPU kernels, in particular machine learning today, have you given any thought to, like, well, first off, have you given any thought to like what this would look like if it were to be, computed on a GPU? Some of the code that you wrote?
Yeah. So I think I'm really interested in re-implementing some of these using the GPU support Chapel has. I think it would be a lot different. I would implement the tensor operations a lot differently. So right now they do like a bunch of like domains, or they do a bunch of like array slicing and things like that. I think instead, there's all of these operations have an analogous, they call it like Einstein summation representation. And those are a lot better for like translating those to the GPU program is a lot easier, and it I think you get more performance benefits because you don't have to section off memory and then combine components and reduce things. You can just each element of the output tensor, you're computing the value of that in parallel rather than doing like some combining process.
Awesome. Yeah, thank you so much. That's all of our time for this talk. Thank you so much, Iain. Yeah, and now it's time for break. I think that there was someone in chat who said something about the performance graph. So if there are any more questions, if Iain's willing, we are totally down to take those during break. But otherwise, go do your thing. Thank you so much.
Thank you.
Thanks, Tess. Thanks, Iain, and thanks, Luca. I'll just read out loud. Paul Satry, our keynote speaker, says, happy to see TensorWork being brought into Chapel. And Gabriel Brown, as Tess mentioned, wow, that performance graph looked great. So great work, Iain.